Hello, in this video I will be showing you my proof for the question 2 of BMO1 from 1996. The question states, for positive integers n, the sequence a1 to an is defined by an is equal to n plus 1 over n minus 1 multiplied by the summation of all the terms of the sequence from a1 to an minus 1. So basically all the previous terms of the sequence. And it wants us to find the value of a 1997, and the first term of the sequence a1 is 1. Now my initial approach was to list all the terms of the sequence and to make some sort of system to show the summation of the terms from a1 to an minus 1. This was a side tangent and it didn't help me too much, but if you see it in the later slides, then the summation basically just means you're adding all the terms where r goes from 1 to n minus 1, you're adding all those terms up. And I tried to use this using series and summation to prove it, but it didn't work. The more useful method was the method using the listing of the sequence terms. Now, going deeper into that approach, I listed the terms of the sequence. Uh, Initially, this was hard because you did 1 and then you had to put that into the next sequence, and then you found 3 and then you got 1, 3, 8, 20, 48. And so on the next slide I'll show you how I made this quicker, and I found a rule that will make this easier. An is equal to 2 times by an minus 1 multiplied by n plus 1 over n. And that rule was helpful. Using that rule, I repeated the process and I got this list. When you have a sequence question, it's the best thing you can do is to look for patterns within the sequence. And so after looking for patterns, I found that the odd numbered terms of the sequence could be broken down into multiples of 2 with some extra factors. So the first term of the sequence of the odd sequence was 2 to the power 0. The second term was 2 to the power 3. The third term was 3 times 2 to the power 4. The fourth term was 2 to the power 8. I was looking at the odd terms because the number they want us to find, the number of the sequence they want us to find is 1997. And that's an odd number. So I was thinking if I can find some sort of nth term rule for this sequence, I can find the value of this odd number of the sequence. So I'd look at an example, say a5. A5 is equal to uh, the number 5 plus 1 over 5 minus 1, which is 6 over 5, multiplied by the summation of all the terms before it. So the term before it, that is a4, is 20. And then you also added on 1 plus 3 plus 8. And I was thinking, if you could find a way to get this list of terms in some formula relating to a4, you could define a5 as a multiple or as a result of a4. And so if you look at the formula for a4, you can see a4 is equal to n plus 1 over n minus 1 multiplied by that sequence. And so you could find 1 plus 3 plus 8, or all the terms before a4, by simply dividing a4 by this fraction. Uh, and if you want to find a5, you just do a4, which is 20, plus a4 divided by 5 over 3, which gives you a4 multiplied by 3 over 5, and then multiplied by its fraction, which is n plus 1 over n minus 1, which is 6 over 4. And you can generalize this by saying an is equal to its fraction, obviously, n plus 1 over n minus 1, multiplied by an minus 1, but in brackets, an minus 1 multiplied by n minus 2 over n, because you have n minus 1 minus 1 and n minus 1 plus 1. The minus 1's on top in this case because you divided it and you flip the fraction. And then the next thing you do is you add on an minus 1, and that gives you the summation. So this bit here is the summation of all the terms before an, and this is the fraction. And this was how I found the rule. And the next thing that I did was I used that rule to find the odd numbers of the sequence. And once I had the odd numbers, I realized that if I could find the 999th term of the sequence, of the odd numbered sequence, I could find the 1997th term of the original sequence. Because if you take, let's say, the fifth term of the original sequence and you divide it by 2 and you add 1, 5 divided by 2, and not add 1, but you round up, then you get the third term of the original sequence, of the odd sequence. And so if you have any value of the original sequence, you could find what value it is in the odd sequence, what numbered value it is. So the 997th term of the original sequence is the 999th term of the odd sequence. I tried finding a relationship between n and n minus 2, so I could find the relationship between every odd number, but this was a tangent that didn't really help me because on the next slide I just look at the numbers and the pattern between numbers. So these are the odd numbers again, 1, 8, 48, the odd numbered terms of the sequence. And I try finding a rule between these numbers, but it doesn't work because you have to see another pattern. If you look at this, you see the fifth term of the odd sequence is 5 times by 2 to the power 8. And the third term is 3 times by 2 to the power 4. And so I realized if you take, let's say, 2 out of here, you have 2 times by 2 to the power 2. And the next term is 3 times by 2 to the power 4. You take 4 out of here, 4 times by 2 to the power 6. So the power of 2 is increasing by 2 every single time, and the multiplier is increasing by 1 every single time. The multiplier is the same as what number of the sequence it is. And so I rewrote the sequence like this. And this is a sequence that I can find a rule for. Because the pattern is that every term of the sequence is n, where n is which term of the sequence it is, multiplied by 2 to the power 2n minus 1. And you can turn that into n times by 4 to the power n minus 1. And because we know which n value of the odd sequence we want to find n999, we can put it in and we find that the value of the odd sequence, the term of the odd sequence that is at 999 is 9 times by 4 to the power 998, or 1998 times by 2 to the power 1995, which means that the 1997th term of the original sequence is 1998 times by 2 to the power 1995. I wrote it like this. It's written like this in the book as well. You don't have to, but it's written in the year form, so it's more like the years. And because of how large the number is, you could just write it in this factorized form.